Initiating System 1. System 1 loaded.
Hi, it's me again, and I welcome you to the world of organic chemistry. I'm Alisa Sofia Badillo, a CM133 student from the section C12. This is my third learning task for Organic Chemistry 1. So, without further ado, let us learn the objectives of this video. We are going to tackle 3 problems that involves mechanisms. We have problem 11.7 from chapter 11, problem 18.49 from chapter 18, and lastly, problem 19.62 from chapter 19. By the way, all of these problems came from Klein's Organic Chemistry, which is the second edition. The problems that we are going to solve are filled with mechanisms. Some are more basic than the others and some are more advanced. Nonetheless, we will tackle everything from the micro steps and then look at everything in a macro view. Let us now have our very first problem, which is problem 11.7. It asks us to draw the appropriate fishhook arrows for each of the following radical processes. So the processes are shown here in this image. This problem is one of the basic concepts that we need to comprehend if we are going to take on complex mechanisms regarding radicals. We will then try to solve for each of the given reactions. This question set challenges us to identify the different types of radical processes involved and to also draw a reasonable mechanism for each reaction. As a reminder, fishhook or half arrowhead curved arrows are used to designate the flow of a single electron, as in a radical. Meanwhile, a full arrowhead curved arrow is only used when a pair of electrons are moving in concert to the same location. In this example, we begin with an organic radical and react it with HBr, which is a strong mineral acid. In order to place the fishhook's arrows properly, we must identify the bonds being formed, which is the CH bond, and the bonds being broken, which is the HBr bond. Formation of the CH bond is shown with 2 fishhook's arrows, one coming from the carbon radical and the other coming from the HBr bond. The latter, together with the third fishhook arrow, shows the breaking of the HBr bond. This is an example of a hydrogen abstraction process. So we must note that the more electronegative bromine ends up leaving with the electron it had previously contributed to the HBr bond. Moving on with letter B, this reaction actually switches the roles around and we start with a neutral organic compound and an inorganic bromine radical. Again, we need to identify the bonds being formed and the bonds being broken. The bonds being formed is the CBr bond while the CC pi bond is being broken. Formation of the CBr bond is shown with the 2 fishhook arrows, one coming from the pi bond and the other coming from the bromine radical. The former, together with the third fishhook arrow, shows the breaking of the CC pi bond. Technically, in here, we are left with an organic radical with the bromine being placed on the secondary carbon in order to form the more stable tertiary radical. This step or process is called the addition to a pi bond process. Moving on with letter C, this question gives us 2 organic radicals as our starting materials. And here we need to take the step called the coupling process, which requires a total of 2 fishhook arrows. Showing formation of a bond, in this case, a CC bond is formed, as shown here. Coupling reaction will always be the nature of the radical process when the starting materials both contain radicals, as here in this example. We are now on letter D. This reaction, if you would notice, has similar starting materials as letter B. Although in this example, the pi bond remains intact in the product. Let's identify the bonds being formed and being broken. In this case, the HBr bond is being formed while the one being broken is the CH bond. Formation of the HBr bond is shown with two fishhook arrows, one coming from the bromine radical and the other coming from the CH bond. The latter, together again with the third fishhook arrow, shows the breaking of the CH bond. This step is referred to as the hydrogen abstraction, meaning to say, because the pi bond remains within the product, it is not addition to a pi bond, but as mentioned, only a simple hydrogen abstraction radical process. Letter E. In this example, we are given with only one starting material, an organic radical to be specific. We can identify that the bonds being formed is a CC double pi bond and the one being broken is the CC bond itself. Formation of the CC double pi bond is shown with the two fishhook arrows, one coming from the carbon radical while the other is coming from the neighboring CC bond. Again, the latter, together with the third fishhook arrow, shows the breaking of the CC bond, the one with the single bond. The chain fragments and a section of the organic material is kicked off as an additional product. This is an example of the process called elimination or elimination type radical process. Okay, last letter, letter F. This reaction begins with an organic peroxide and shows the products to be a pair of organic radicals. Organic peroxides are normally quite unstable and only need a little heat in order to undergo a reaction. The two fishhook arrows indicates the breaking of the OO bond, and since the bond that broke in the starting material was between two identical atoms of the same element, which is oxygen, this reaction is what we call the homolytic bond cleavage. We are now moving with our second problem. The first one is quite lengthy because it has a lot of subsections. Nevertheless, the following problems that we are going to solve do not have any other sub-questions, but the mechanisms themselves would be more complicated than the ones we did earlier. Okay, let's proceed. For 18.49, we must predict the product of the following reaction and propose a mechanism for its formation. Reaction of a benzene derivative with sodium metal and ammonia and alcohol is called the Birch reduction, and it leads to a cyclohexa 1,4-diene derivative. Let us now proceed to the mechanism itself. As a group 1 metal, sodium has one available electron in its valence shell. This electron attacks the tetramethylbenzene starting material, causing the rings pi electrons to rearrange so that the negative charge doesn't reside on a methylated carbon. Recall that methyl carbons are electron donating via hyperconjugation, and so having the negative charge reside on a methylated ring carbon would be less stable than the indicated arrangement. This intermediate also contains a radical, making it a radical anion. Quenching of the anion via proton abstraction from the methanol gives us a radical intermediate, as shown here. Moving on, a fresh atom of sodium can then donate its electron to this radical, resulting in a carboanion as shown here. Pushing forward, quenching of the anion via proton abstraction from the methanol gives us this final product. So, that is quite a handful, but let us summarize the mechanism and look at it in a bigger picture. So, this is the entire mechanism itself, and the reagents indicate a Birch reduction, which is believed to occur via a four-step mechanism, as seen here. In the first step, an electron is transferred to the aromatic ring, generating a radical anion, which is then protonated with methanol functioning as the proton source. Another electron transfer process followed by a proton transfer result in the formation of the 1245 tetramethyl 1,4-cyclohexadiene as shown. Notice that the four positions bearing the electron donating alkyl groups are not reduced. Then, the two positions without electron donating substituents are reduced, allowing us to have this final product. There we have it for the second problem, so let us now push through the last one, which is problem 19.62. In here, we are asked to propose a plausible mechanism for the following transformation, which is shown here in our image. Recall that the lone pairs of electrons and oxygens are nucleophilic and can abstract a proton from the highly acidic sulfuric acid. This protonated alcohol group could leave as a neutral molecule of water, which would place a carbocation in the resulting alkyl fragment. That gives us a good place to start our mechanism. The starting material is benzene, and the product exhibits a disubstituted aromatic ring. This will require us two successive aromatic substitution reactions. The reagent or the diol is not a very strong nucleophile, nor is it a very strong electrophile. However, in acidic conditions, the diol exists in equilibrium with a very powerful electrophile, a carbocation, as shown here. To specify, one of the OH groups can be protonated, giving an excellent living group and followed by the loss of water. That gives us a stable tertiary carbocation. Since the reagent is electrophilic, we can expect that the reaction will proceed via electrophilic aromatic substitution. Accordingly, the aromatic ring attacks the carbocation to the given intermediate sigma complex. Putting it simply, the tertiary carbocation is attacked in an electrophilic aromatic substitution by one of the pi bonds of the benzene ring. So, after the attack, we can have the resulting intermediate sigma complex as mentioned. Moving on, the resulting sigma complex is then deprotonated by a molecule of water to give a stable neutral intermediate. We already said earlier that we would be needing two successive aromatic substitution. Thus, we need to repeat the process all over again, except this time, the reaction will proceed in an intramolecular fashion, closing the ring. So in here, we are showing the process that we made earlier or the similar mechanism. The result though will be a closed ring as follows. To recap, we have to note that there is still an alcohol group present in the molecule. In a similar fashion to our first mechanistic step, this alcohol is protonated by a molecule of sulfuric acid. Loss of water then gives us a tertiary carbocation. Another electrophilic aromatic substitution reaction leads to a sigma complex, which can be deprotonated by a molecule of water. This regains aromaticity, which is a large positive driving force. Finally, we will be able to get our product, which is a 1,2-disubstituted benzene. To tie everything up, since the aqueous acidic conditions are employed, H2SO4 is generally dissolved in water. The proton source throughout the mechanism has been H3O plus and the base has always been H2O to be consistent with the acidic conditions. If we would view the entire mechanism in producing the 1,2-disubstituted benzene, we will have this. Well, that concludes our learning task 3, and I really hope that you have learned something from this video. Nonetheless, if you have any questions at all, just comment down below our discussion board or you can email me in this address. That's it. Thank you so much and good day.